solution. And so this started this work about 2 years ago, and we are beginning to get some results, but of course there is a big gap between the results that we get and what you can apply in practice. But in any case, I think this is an area that is quite important. I am convinced of that, and where there is a lot of interesting work to be done. So I'll try to convince you of that, and that will be my main message. Okay, so this is the outline of the talk. I will start with some motivation. So what is the vision behind the work? And as usually, you paint a glowing vision, and then you go down to a few concrete problems. So I will go down to three specific problems, which cover three aspects of this big vision. And the three problems have to do with service differentiation. So how do you separate the different types of services? Then looking at the complexity of the actual internet, the fact that it is operated by many providers, and those providers interact in complicated ways. So how do we model this? Then I will look at one more focused aspect, which is the Wi-Fi situation, what's happening in Wi-Fi, and how can we improve the situation in Wi-Fi. Then some conclusions, and then I will mention some references. So if you have questions along the way, I think we have time. I don't have hundreds of slides to show you, so let me start with the motivation. So you first realize that some users would pay for better network services. If you talk to users, they will say, oh yes, there are many applications. So occasionally we have to transfer big files. We have to synchronize our databases. You go to Bank of America and they will say, yeah, regularly we have this synchronization of the user databases. Right? So those are big files, and we would like that to be improved. So we do network backups regularly, right? And this is always inefficient and doesn't work well. Regularly, the notion of video conferences comes back. So you work on the West Coast, and once in a while you work with companies that have branches on the East Coast, and they will go to a special room where they will use 4 ISDN lines to do video conferencing today. And those 4 ISDN lines give you about 600 kilobits per second. It's not much, right? It should be easy to push that through the internet, given the glut of bandwidth that we have. But no, they go to those ISDN lines to do this, and the result is okay, but it's not great. This presentation could be streamed, right? I don't know if anybody would watch it, that's another problem, but it could be made available in real time to many people. These services are not available today on the internet. Well, you can try to use NetMeeting, and usually after a while you give up, because the video aspect of NetMeeting doesn't work, so you end up using just the synchronization of the slides, but you cannot use the nicest features of those applications. In a related context, a big fraction of the infrastructure is poorly used. So, for example, now at home I have a Wi-Fi network that is not being used, and the neighbors could easily use it. I would not suffer from it, right? So, and that's the case around the country. You have many points where you would have access to a Wi-Fi network, but you cannot have access, and there are good reasons for it, security and others, but also economic incentives. Okay, so why is this situation like that? Well, is it because there's a lack of bandwidth in the network? For a long time we have heard that bandwidth would solve the quality of service problems in the internet. This is not really happening. So there is a lot of bandwidth, so there's not a problem. Is it because we don't know how to provide quality of service? Let's say if I want a video conference, I want to guarantee a certain throughput and a bounded delay. Is it true that we don't have protocols to do that? Well, you look at the RFCs of the IETF, they are full of various proposals that have been made, and some of them make a lot of sense. They would work. Is it that we like protocols for requesting services, for provisioning services? Well, we have RSVP and many variations of that. So those things exist. I think that the bottom line is that the economic incentives are missing. If you ask the network provider, you say, why can't you provide me a guaranteed throughput on my cable modem or on my DSL line? They will say, well, let's imagine that I do it, right? Then the bottleneck would be spent. It will not be the local access. So you will not see that you are getting good quality from me. right? So why should I provide it to you? The other players will not provide it. And then you ask the other players, say, why don't you provide it? They say, well, there's no mechanism for us to get compensated for this. There will be some extra cost, management cost. We have to turn on some features in the routers. That takes some time. There's some overhead that will be associated with all this. But there's no mechanism to control the quality of service that the various flows are getting in the network, and therefore we cannot charge for them. All right, so what we need are economic incentives, so we need a billing mechanism. We need a way to do a fair revenue sharing among providers, and this is, I think, an important point. So it's not enough to bill customers, but you have to find a way to redistribute the revenues fairly among the network providers. And there are many network providers, right? So if you have a single post office, a US post office, you put a stamp on the letter, and the post office will get the revenues. That's easy. The situation becomes much more complicated when part of the mail is carried by the US Post Office, then is handed over to the French Post Office, right? Then you need a way of recharging. And in the case of the Post Office, even in the telephone network, all that has been worked out very carefully. So we know that when you place an international phone call, we know who is getting what fraction of the bill, right? So that has been settled. And in the telephone network case, it's easy because every phone call is monitored, right? But in the internet, the magic of the internet is that you can build a network without having all this control information. So how do you keep the simplicity, the lightness of being of the internet and make it compatible with these objectives? So that's very challenging. So you need scalable protocols, right? So it's not enough to, on paper you can design a scheme where you will do the billing and distribution of revenues. How do you make it scalable? And scalable in the internet sense, right? And this mechanism should provide the correct incentives. And I will tell you when we look at models what that means. And it's not quite easy to get, right? So you should, for example, discourage cheating. So if you provide, if you are paid for quality of service, your incentive would be to pretend that you are providing more than what you are actually providing. That would be cheating. And the end user might not be able to trace back the problem to you, right? So how do you design a protocol that will prevent this situation? And also it should promote upgrades of the network. And that's very important, as you will see in the models, that it's not obvious that those schemes will encourage and provide the incentive to the various network providers to improve their network. So the vision is very simple, right? If you improve the service quality, you need revenues to do that. But once you improve the service quality, then you will increase the revenues and you can feed on itself. It's a very simple model. All right, so let me describe at a high level the three problems that I would like to spend some time on today. The first problem is service differentiation. So you have different types of qualities of service. You have a slow mail and you have fast mail, right? So you would like to be able to segment the market so that the users who are willing to pay for the first class can get first class. They will pay more than if you pay just a regular mail, bulk mail, right? So why does it make sense economically? Well, why is there a first class on a plane, right? Because maybe the people will pay 10 times more for a seat that occupies maybe twice the space in the plane. So clearly it's economical to extract this willingness to pay. We make more profit that way, right? And the same thing is true for communication services. So the idea is to capture the willingness to pay for better services. How do we do this? And I will discuss some models of that. The second issue is the issue of a multi-provider network. This is a rough sketch of how the internet looks like. You have different tiers of network providers. You have those backbones, the Sprints, the AT&Ts of this world. Then you have the local access, like the SBC or Verizon or whatever, right? And then you have the customer networks. So you have those different levels. And to establish a connection from A to B, you need all those guys to cooperate and to participate in the service. So how do we do this? How do we provide the incentive for all the players to do the right things? So that's the second problem. The third problem is to do with Wi-Fi access. And the idea is that if you can solve this Wi-Fi access by providing incentive to open up the private networks, then you might have ubiquitous access to Wi-Fi everywhere. Right? So at least you might go in that direction. So for each of those problems, I will look at models, simple mathematical models, and try to understand the structure of those problems. Right? Okay, so the first problem is surface differentiation. So I will describe a model of this surface differentiation, give you some examples of what the problem becomes and what the features of the solution are. And then I will make a proposal for how to avoid the bad features that you see in the solution. Okay, so this is joint work with Linai Hay. Okay, so let me describe the model first. How do you provide service differentiation? So here the model that we have in mind is very simple. It's a priority service. So think of DiffServ. You buy a DiffServ router from Cisco. There's a differentiated service feature where you can classify the streams and then you can say this is high priority, this is low priority. Right? You can do more sophisticated things, but this is a basic service. This is one simple scheme. Right? So in this model I have two users, Alice and Bob. Right? And they will choose high priority or low priority. If they choose high priority, they pay P1. They choose low priority, they pay P2. And then they get served according to this priority scheme. Right? So each user will choose the service class, so P1 or P2, that will maximize his or her net benefit. What is the net benefit? Well, you subtract the cost of the service, P1 or P2, and then you look at the value of the service to you. The value of the service in our model is a function of the delay that you will face. So the delay that you will face will depend on the service class. And the idea is that if you get a low delay, then you are happy. If you get high delay, you are less happy. Right? Now the question is whether it makes sense to buy the high priority service, whether the increase in satisfaction makes up for the increase in cost or not. Right? There are two possible outcomes of this game, right? Either Alice and Bob will choose the same class, or they will choose different classes. If they choose the same class, they will face different delays. So the notation is that if I choose high class, high priority, and the other one chooses low priority, the high class will face a delay T1, the other one a delay T2. Okay? If they both choose the same service class, they will both end up in the same queue, whether the first queue or the bottom queue, and they will see the same delay that I will denote by T0. Okay? So T1 is the delay for high class when the other class gets T2, and T0 is when they choose the same service class. Very simple model. Now, what will happen in this situation? So we see it as a game, because you have two players, Alice and Bob, and they have conflicting objectives. So they will both be selfish and choose what they prefer, right? So what happens here? Okay, so again, this is a picture, and this is the matrix of rewards. So this is standard game theory, but let me go through the model. So if you are not familiar with it, you will see what game theory looks at when you look at a game. So here you have a matrix that shows the two possible decisions or actions of the two players. So Alice can go high class or low class, right? And Bob can go high class or low class. And then for those four combinations, I wrote down the reward of Alice and the reward of Bob. So the reward of Alice, if they both go to high class, Alice will get a reward F1, so this is her utility, when she gets a delay of T0, right, and she pays P1. And similarly, Bob will get F2 of T0 minus P1. I assume here that F1 and F2 may be different. Maybe Bob prefers low delay and Alice doesn't care.
Yeah, so when A and B are in the same queue, you assume there's same delay.
Yes.
Why is that?
Well, let's assume a generic model where the arrivals are similar.
So the delay is not caused by the transmission of the service delay request, it's just caused by the other traffic in the queue.
Yeah, so the delay is caused by the queuing of all the packets in the queue, and if the traffic is similar, is exchangeable, right? Then they will face, by symmetry, they will face the same statistics of delay.
You're not considering the actual transmission time of the service, the A and B service, the request itself.
Not the processing of the request. I'm looking at the delay faced by the data as it goes across, right? So let's say you have two video streams, and they will go into the same queue, they will see the same delays, because they will experience the same queue. Yes,
In other words, the only difference between two tunnels is the mechanism at
the service here. So, yeah, so you have two queues, and then you give high priority service.
the difference is only there.
The difference is only there.
Otherwise, they're the same.
Yes, you could imagine that they are sending exchangeable traffic. If you make other assumptions, you make personal assumptions, then it becomes obvious that the packets will see the average distribution in the queue, and they will see the same delay. All right, okay. But their utilities might be different for the same delay. Similarly, if they go to the second queue, they will see the same delay, right? But the price will be less, it will be P2. And then if they say that Alice goes to the low priority class, and then Bob goes to the high priority, then you see Alice will face the delay T2, the longer delay, and Bob will face the smaller delay, T1, okay? So this is called the payoff matrix of the game. You look at all the possible strategies, which are the decisions of all the players, and you see what everybody gets. So this is a payoff matrix. And so this is standard, very standard stuff. So this is A's benefits, this is B's benefits. I will assume that T1 is less than T0, less than T2. I will assume also that the utility functions are non-increasing. So if the delays increase, you are less satisfied, right? So let's look at some examples to see what situation may arise. And it's not that surprising, but still it's interesting to look at what happens. So here I chose the case where the utility functions are the same. F1 is the same as F2, and this is the utility of having a low delay, the utility of having an average delay or a long delay, and these are the prices. And these are the numbers you get, right? For Alice, so Alice in red and Bob in blue. And let's look at the situation, a scene, for example, from Alice. Let's imagine that she thinks that maybe Bob will use the low latency, the low priority class, right? So Alice is choosing between high and low, and she's thinking, well, let's imagine that Bob will use the low priority service. Then what are my choices? Well, if I use the low priority, I will see a delay, a given delay, a utility of 9 minus 1, right? So Alice says, if I use the low priority, I see a utility of 8. If I use the high priority, I will see a utility of 10. So I prefer 10. Right? Now she says, well, but maybe Bob will use the high priority class. Right? So we are in this column now. And then she will compare what she would get in the low priority or high priority. And again, she finds that she would be better off using the high priority. And by symmetry, the situation is the same for Bob. Bob will do the same reasoning, so they will both agree that no matter what the other guy does, they should move to the high priority class. So what happens then? Well, this is a so-called Nash equilibrium, where acting selfishly, they will converge to the strategy of choosing the high priority class. What you see is that they get the same delay as if they were both in the low priority class, right? So, but they are paying more for it. Right. So just because they know that their delay will be reduced by going to the high priority class, no matter what the other guy will do, they say I should have the high priority class. So they both end up being stuck in this situation where they pay the high class and they get the low quality service, in fact, right? Because they are in the same queue. This is an example of a prisoner's dilemma that occurs in this situation, right? Okay, so nothing very new, but it shows that if you provide service differentiation with a priority mechanism, there may be situations where the result will not be efficient for the users. You don't know what their utilities are, you don't know, right, what they will do, but it might be that they will end up in a prisoner's dilemma, which is not very desirable for the consumers, at least. Right? This is a slight variation on the problem where now I assume that maybe Bob and Alice have different utilities, slightly different utilities for the different delays, which is quite possible too, right? And then you do again a little look at the payoff matrix, and you find that in this case there is no equilibrium. That if you are in this situation, both low priority, then Alice will decide that she should move to high priority. And if Bob is in the low priority and Alice in the high, then Bob will decide that she should move to high priority. If they are both in the high priority, then Alice will say, oh, I should move to low priority. And in this case, there is no equilibrium. This game has no equilibrium, right? There is a randomized equilibrium, which is hard to justify when you place a video call, right? It's more fuzzy. So it just shows that providing priority service may not lead to what you expect. It may not lead to the correct market segmentation. You can extend the situation to many users. Yes?
I have one question. Because normally people don't want to have the same high priority traffic, high priority traffic all the time. They probably would like to switch between high and low all the time. Is it possible that at least have information about Bob, that Bob might have enough would like to have high priority traffic for 30% and 70%? We want to have like...
Yes, that is possible. So in the previous model, it was a very simple model with 2 players, 2 users, and each has only 1 traffic to send, right? This is a case where I have a mixed population, a huge population, and there's a fraction of users or fraction of traffic that requires high priority, the others that will require a low priority. And we model that by saying that the utility is parameterized. So the desire to have low delay is parameterized by some parameter theta, which is a willingness to pay for quality. And you make a similar analysis in this situation. It's a bit more complicated, but you also end up with a situation where if f is a concave function, and if you use strict priority scheduling, then you end up in a very undesirable situation again. You will have an unstable equilibrium that would be good, but it turns out that it's unstable and you will move to an inefficient equilibrium. So the situation is more complicated, and I will refer you to the paper for that. But it shows that in a more complex situation, which is not that naive, where you have many users and a willingness to pay that is more complicated, then the priority service, again, has undesirable features. So this is not a good way to do the market segmentation, typically. Right? So we make a proposal, and we say, well, these are really not desirable ways of doing things. So we propose a scheme that is quite different. And the idea is that we guarantee a quality of service. Instead of fixing a price for the class of service as we did before, and then you end up with a quality of service that depends on what all the players do. So you remember in the case, Alice had to worry about Bob joining the high priority class, right? Because then the delay in the low priority class would be very long. So because of this uncertainty about the quality of service that you get for a given price when you do priority scheduling, instead we propose a model where you will guarantee a quality of service, but the price will adjust depending on the demand. So it's a form of congestion pricing, if you want. So there is a lot of demand for this airplane seat, then you pay more. If it's off hours, then maybe it's a cheaper seat, but you still get the quality that you expect. And this avoids this coupling between the users about the quality of service. So it's an indirect to the price, but then you know your willingness to pay. So, and if you do that, you get a situation that is much better. And you find that there is a Nash equilibrium, so we don't have the problem where things are oscillating all the time. Also, the equilibrium approximates the outcome of a Vickery auction, which is a fair auction. When you buy a work of art, you do a Vickery auction. So this is a bit similar. It has similar properties, it has nice features. And also, you can show that if the arbitrator knew the utilities of the users, which is something that the operators might be able to measure over time, then this auction would lead to a socially efficient use of the network. So not only the users would have an incentive to play the game correctly, declare their willingness to pay for the service quality, but also it becomes socially an efficient way of using the network. And but unfortunately, the analysis is a little bit more complicated, so I will refer you again to the papers that we are writing on this. Yes?
The reason that you're getting more socially beneficial or better, socially better equilibrium, is that because the users are losing market power?
That's right. That's right. So because of the size of the game, so when the game becomes very large, so now the auctioneer is able to fit the demand well into the network capacity. That's a good observation. Right. The multi-provider network model is quite different. So before we had a single router, right? It's a very Mickey Mouse type model of a network. In a real network, this is very complicated. So again, this is joint work with Linai. So the picture is like that. Many network providers, they should all get compensated for providing services. Right? So how do we do this? And you want a scheme where each provider has a selfish interest to play the game fairly and to help the network. So how does this work? So I will first do a simple model and then look at the Nash game model. Again, it's a very traditional Nash equilibrium model, and see what happens in that case. And again, you will see it doesn't work quite the way you would like it to work. Then we will propose a different protocol that seems to avoid those difficulties. So the model is a pricing per packet. So I'm sending a packet from A to B. Maybe I'm setting up a video conference call between Maryland and Berkeley, and I'm setting up the connection. I'm going to two providers. You can extend to a large number of providers, and each one will charge for the transmission of the packet, right? Reasonable. So P1 is the amount that the first provider will get per packet. P2 is the amount that the second provider will get per packet, right? Now, so the end user will be charged P1 plus P2. The demand, of course, will depend on P1 plus P2. If P1 plus P2 is too high, you say, well, sorry, I will not connect. I will use something else. I will go back to my ISDS line, ISDN line. So you have the edge routers need to do the marking, to put the stamps on the packets. So let's look at this as a game between the different network providers. So in this case, the players are the network providers. They are no longer the users. In the previous model, the users, Alice and Bob, were the players. Here, the players are the network providers. Maybe AT&T and Sprint. Right? Those are the guys who play the game. So there's a demand that is a function of P1 plus P2. I charge P1, and I will charge P2 for this link, P1 for that link. Okay? So we take P1 plus P2. There are capacity constraints. So this link has a capacity of C1 packets per second, and this is a capacity of C2. If the capacity were infinite, the problem would be quite different, but it's never infinite. So this is the situation seen by provider 1. Provider 1 would like to maximize P1 times the demand corresponding to the price P1 plus P2. Okay? So if we charge P1, the other one will charge P2, my revenues will be P1 times the rate of packets for which I can charge P1, the demand. There is a capacity constraint that I face, where the traffic cannot be more than C1. Okay, so this is the objective function of player 1. Player 2 is the same, but now it's P2. It's very similar. So these two objective functions are conflicting again, because if I increase my P1, well, the demand will drop. It will also reduce the revenues of the other player, and so on, right? So those two guys are caught in a game, and we can try to study what happens to the game. So it's a game between two providers. There are many different solution concepts that we can adopt, as it is the case for all games like this. And it seems that traditional solution concept is a leader-follower concept. So where the big guy, AT&T, will decide the price, and then the lower players will then decide on the price based on the price of AT&T and so on. So those are called leader-follower or Stackelberg games. But in a big network where you have so many providers, it may be more natural to model it as a game, a symmetric game, where everybody is an equal partner in the game. Right? So then you end up with a Nash game. So let's study the Nash game. And you study a Nash game like this, and you find that the result is disappointing. First, the bottleneck providers, so the providers that have the smallest capacity, will get a bigger share of the revenues from the users. So which is a bit paradoxical, right? So if I'm the bottleneck link, I will get paid more.
You normalize by the capacity, or is it more shares?
It is, so the capacity is enters as a constraint for each player, right?
So when you say get more shares, it means?
No, it means the absolute amount of money that they get is more.
Absolute amount.
Right, yeah, to get more. It's not a fraction of the capacity, in proportion to the capacity. Just the absolute amount they get is more, right? Which is clearly not very desirable. Moreover, the bottleneck guy may not have an incentive to upgrade the capacity. So by increasing the capacity, his total revenues may go down, which is not good, right? This is very bad. And also the efficiency of the network. So the revenues per provider will drop very quickly. So if you have many players in the game, then they divide up the crunch essentially, and it's not a very good game for them to play. They are not very motivated to play a game. And you can do the analysis for complex networks, and you can show all those properties. So this is not very good. So we propose a slightly different model. The model raises some legal issues, but I will forget about that, and I will just look at the mathematical problem. Right? Yeah, okay. So how do we improve the game? And then we will look at a model of how to improve the game, what are the optimal prices on this new game, and some examples. So there are many different ways of changing this game. Clearly the Nash game does not work, right? It has the wrong properties. So you could try to centralize it. You go to a public utilities commission that will fix the prices, and then you will debate with them for the prices. But it's very complicated, and we know the problems with this approach, and there's a push to deregulate because this is not efficient typically. Right. Or you can look at cooperative games where the players different players will try to talk to each other and signal their willingness to charge different prices. And then you could have a mechanism design approach where the users are bidding and for services, and then they get charged based on their bids, like an auction type game. So there are many ways of modifying the game. So our approach is fairly simple. We want to design a protocol that has nice properties, that is in the provider's best interest to follow. So all the providers say, oh, these are the rules of the game. Yeah, I like the game, and I will make money with it. It's fair. I will follow the protocol. And also, it is suitable for scalable implementation. So it does not require a lot of state keeping in all the routers about all the flows, which clearly is not feasible. Right? Okay, so what is the model? Well, same model as before, right? But we will change the revenues that the users get. And in this model, what we say, okay, we will just collect all the revenues from the users, so they will be charged P1 plus P2. The demand will be D of P1 plus P2. The total revenues will be P1 plus P2 times the demand, and we will share 50-50. Okay? So it's a revenue sharing model. Okay, so the charge is carried by the packet, so every provider will see how much is being charged. So you can divide the revenues. There is still a capacity constraint. C1 for provider 1 and C2 for provider 2. Now you could argue, well, why 50-50? This may be a small guy, this may be a big guy. You can change the model of different sharing fractions, so that does not change the nature of the solution. Okay, so what are the optimal prices for this game? And this becomes interesting. This is a bit similar to an optimization problem with many constraints, right? So you have all those constraints, capacity constraints of the various links that you can reflect as a shadow price for the congestion on those bottleneck links. Right? So it's an optimization with constraints. So you can look at the dual problem, right? And there will be a shadow price that you have to pay for violating the constraints or the active constraints. So you can do the model, and then you find that the price, the optimal price that I should charge, is a function of some shadow price and I that reflects the congestion at that link. So if your link is congested, you should charge a price for the congestion. Right? Then you do the analysis of this dual problem, which has some equations, and these are the properties that you get. For any feasible set of the shadow prices, there is a unique solution, and the solution is like this. On the link with the largest mu, which is mu star, then the price is pi star, which is n times mu star, plus some elasticity function, g of pi star. Right. But on all the other links, the price is 0. So what this says is that only the congested link will set a price. Right? The other constraints are not active, so they are not congested, and there is no shadow price in this optimization problem. Okay, so what happens then is that you can look at this as an iterative process where I find the mu i's, the shadow price, I'm looking for them, I postulate some shadow prices mu I solve for the pi's, And then the demand will follow, and then we keep on iterating in this loop, and that we should converge to the equilibrium. So what we have taken is the original game, which was a nice game on the prices, and we have converted it into a nice game on the shadow prices, on the mu I, the congestion prices. And you can show that there is a nice equilibrium for this game, and moreover, there is a simple protocol for computing it, and I will show you the protocol. But before I do that, let me compare with the traditional congestion problem that you have in the network. So you know that TCP is a way of sharing fairly the congested links in the network. And the way you do that is by marking packets along the way when in routers that are congested. So when a router is congested, it will put a mark on the packet, maybe explicit congestion notification, right? Or it will drop some packets, which will signal to the source that you are going through congested links. The marks add up on all the congested links. So for example, the loss rate that I face will be the sum of the loss rates of all the congested routers, right? So the way I will react is to a price, the congestion price, that is additive in the congested links. In this case, the problem is different. Instead of having an additive mark that you have in the congestion problem, you have a maximum mark. We have seen that only the congested link would mark, the others will not mark. So if you think of this in the traditional framework of TCP or Kelly and so on, where you try to maximize the social welfare of the network by regulating the flows in the network, then the way you do it is by having shadow prices that are additive along the links. In this game, which is no longer a social welfare maximization, but instead it's a selfish maximization by the providers, then you get a similar story, but the marking, instead of being additive, becomes a maximum marking scheme. So I'm a router, and I see some level of congestion in my link, and I will compare the mark that I would like to put on the packet to the mark that is already there. If the mark already there is bigger than what I want to put, I will not change it, right? If my congestion is more than what the packet has seen so far, then I will mark the packet, right? So this is a maximum marking, yes.
If I look at the structure of the solutions, the PI stars,
Yes.
the structure is very similar to the case where the price function is very responsive to the demand.
Yes, that's right. It turns out to look that way, yes. But this is true for even if the demand function is not very responsive. So this is a general result, right? So it's easy to understand if it is very responsive, but it's also true if it is not. So it does not depend on the actual price depends on the elasticity, right? But even if the elasticity is arbitrary, you have the same structure. So if you compare the solutions, then you can see a trade-off between efficiency, social efficiency, and fairness to the different users. Moreover, you can show that the solution gives an incentive to upgrade. So any bottleneck link will increase its revenues by increasing its capacity, which is a nice, desirable feature, because eventually all the network providers will try to improve the network to respond to the demand, which is a desirable objective. So it's efficient when the capacities are adequate. So what is happening is that if there is no bottleneck, so it turns out that maybe the demand is saturated. You cannot saturate the network because the demand is met. Then you get the same result as if you had a centralized allocation of the flows. So it's efficient socially when you have removed the bottlenecks. And also the revenues per provider will strictly dominate what you have in the nice game. So it's good for the providers. The providers should be happy with this version of the game as opposed to the selfish nice game, because they will make more money. And then you can design an algorithm that will compute the muse in a distributed way. And it looks like this, right? So this is the mark that I compute at time n+1, and it's a maximum of 0 and the mark I had before plus some step size times the difference between the capacity and the utilization. And then you can imagine a scheme that will do that. And the way the scheme will go, let's say I want to start my connection, my video connection with Berkeley. I start sending the packets. The routers are updating their marks on the packet. Then the packet comes back and tells me what the price will be. So the edge router of my local provider will give me the price. Based on the price, I will accept the connection or I will reject the connection. So there is no state that must be kept inside the routers. The only thing that they need to see is calculate the local price according to this formula. So it's a fairly easy calculation. You don't remember the state per flow. Right, so it should be a scalable solution. Let me give you an example. So this is a very simple example where I have only 3 providers and I have 4 connections. And you run the algorithm, and this just shows that this converges, and it converges to the right thing. Right? So these examples are what they are. But it shows also that the price on link 2, link 2 has a high capacity, and it's not a bottleneck, so the price on that link is 0. Right? But link 2 will make revenues, because it will share the revenues of the packets that it carries. Right? But so, and then also here link 1 is congested, it has a small capacity, the price is the highest, which doesn't mean that it will make more money. Remember, you divide equally the revenues from the network, but it will have an incentive to upgrade its capacity. And eventually you will go to a situation where the flow is limited by demand and not by the capacity. Yes? So this is time. These are steps in the evolution of the algorithm.
Iteration number?
Iteration. In the algorithm, you remember the formula, we have looked at a discrete model for the algorithm, mu I of n plus 1, so this is n on the axis.
Okay, so similar case, for example, the connection length is small.
Right. So if the connection duration is small, do you have the time to learn the price? So the way we think of it is that this is a very big network. There are thousands of connections, right? And then you learn the price that you should charge to connections. And there's so much traffic that you adapt all the time. If the demand changes slowly, then your prices will adjust slowly, right? But yeah. So we don't think the time scale should be a problem.
The algorithm that you presented shows that every ISP knows how the sharing is taking place.
Yes, that's correct.
What happens if you have a malicious ISP?
Right.
That applies a different rule.
Right, so it could be that one ISP says, I don't want to play your game, I will do something else. Then what is happening is that you end up with one player playing a nice game, and the rest playing this nice cooperative game. In that case, what will happen is that those cooperating will form users or providers will form a coalition against the other one, and again the incentive will be for this individual guy to join the coalition because his revenues will be higher than in the nice game, right? So we think that this has the right features that it should eventually, in the long term, converge to the right situation.
One thing I noticed is that for each service provider, you have only one choice of a downstream service provider.
Yes.
Now, if you have a choice, would you expect the same kind of results, especially in the non-cooperative setting?
Right. So, Richard.
More or less a monopoly.
Right. So we have taken the model where the routing is not under the control of the users. So we are doing the usual IP routing, right? If you have the choice of routing, so if you could do source routing and say, no, I don't want to go to Sprint, I want to go to AT&T, then there will be a competition for attracting customers. And then the situation is quite different. And there are some recent papers on that problem by Lafont and some other people that show that those providers, if they are not careful, will be driven down to zero profit, right?
Well, absolutely.
Yes, it's the same in
It's a monopoly.
Yes, yes. So how to avoid a situation we don't know. Right.
Who pointed this out to the paper again?
I believe it's Lafont. I can give you the reference. All right. So in remaining time, let me talk to you about the Wi-Fi pricing. So let me discuss the motivation again, then explain two models for the problem of pricing Wi-Fi access. So this is joint work with John Musacchio, who's also an extremely bright student. Motivation. So the idea is that there are many Wi-Fi access points that are not being used, and there are many users who would be happy to use them. So you go sit to a public bench or to have a coffee somewhere, you are in range of some Wi-Fi network typically, right? So how do you provide access? So if we can provide access to those networks, then everybody is better off. Right? So how do you do that? So the idea is to do some payment to the Wi-Fi owner, so that you will say, okay, when I'm not using my Wi-Fi network, I can charge a few dollars a day, just for other people to use it. We assume that you can resolve the security problems, right? We are not working on security. So if that is the case, then it should be good for everybody. Now it's understood that if you need your Wi-Fi access point, you will have priority and the other users will not be able to use it. So that will not affect your utility for the network. So how do we do payments? And there are various payment schemes that you can use. What we have in mind is a micro-payment scheme, where the time is decomposed into little time slots. Time slots may last maybe 10 seconds. And for time slot n, the base station will propose a price, Pn, and then I will either accept the price or I will walk away. So if suddenly the network becomes too expensive, I walk away, I go somewhere else, or I try to connect to another network. Right? So it's a micro-payment scheme. And there are various papers on how to do that efficiently with a limited overhead, and so I will not go into that, but so that's a feasible solution. So two models. So how do you model this situation? So one is a web browsing model, the other one is a file transfer model. In the web browsing model, so this is the client, this is the base station that you don't know, you don't trust, and the utility of the client is proportional to the duration of the connection. So as you keep on browsing the web, you derive some utility for it. And you plan to stay at this bench for maybe k time units, k time slots, right? And after k, you go away. The actual duration of the connection may be n, right? So maybe you will drop out of the game after n steps, which may be smaller than k, and then your utility stops. Now there is some utility factor, u, that is some random variable. So the base station does not know how eager you are to browse the web. Maybe what you are doing is just passing the time waiting for a bus. Or maybe you are reading the news, and then it's more valuable to you. So there is a profile, a typical profile of a user that is characterized by some distribution u. And the base station knows the distribution of the random variable u, but does not know the actual value of u. Alice probably knows her value for u, right? Similarly, Alice knows k, but the base station does not know how long Alice plans to stay there. So this is an example of a game where you have asymmetry of information. The user, the client, knows more than the base station. And somehow in those situations, it's like buying a used car, right? The dealer of the used car knows more about the car than the buyer of the car. And typically you get taken advantage of in those situations, right? It's a well-known paper, Market for Lemons, where it won a Nobel Prize. So this is a similar situation. Market for Lemons. Lemons being used cars. The base station utility is P1 plus P2 plus Pn, the amount of money that it collects. We do not model the cost, it's assumed to be a fixed cost. Right? This is the utility. You should subtract the payments to get the net utility, the net satisfaction. And if the net utility becomes negative, then it's not a desirable gain for you. All right, so what can we say about this? Well, we can derive the equilibrium for this game. So now the concept of equilibrium is a bit complicated because there is this asymmetry of information, there is randomness in the perf matrix. Remember in the Nash games we had before, the perf matrix was known, just numbers that you knew. Here you don't know, right? The base station does not see the same thing as the client. Right? So there is a concept of a Bayesian equilibrium for this Bayesian game, this random game. And also it should be perfect in the sense that it's a dynamic game. You are playing it only one time, but you keep on playing it. So the strategy should be optimum for every possible continuation of the game. So if you have played the game for 5 slots, your strategy should still be the best for the remaining slots. So that's the notion of a perfect Bayesian equilibrium. And you can show the following result. The result is very simple. The client will accept to pay as long as the payment per slot is less than the utility per slot. So it's a very myopic strategy. My utility per slot is 0.7. I'm being charged 0.6. I say, okay, I accept. I'm being charged 0.8. I walk away. It's a very simple strategy. The base station will choose one fixed price. And this is same price at all times. And the price, you find it, you maximize P times the probability that the utility is bigger than P. So think of the game being played one time, and you charge P. The user will accept if the utility is bigger than P. So this is the expected reward that you get if you charge P. So myopically, you optimize over P, as if the game was only a one-shot game. This is surprising. Why is it surprising? Well, it's surprising because you are learning about the utility. Let's imagine that the client connected for a price of 0.5. Then the base station knows that her utility is more than 0.5. So you think, well, based on that, I can raise my price to 0.55, right? And so it's a bit surprising. We found it surprising that the strategy, the optimum strategy, is a fixed price, which is very comforting. Yeah, it's a simple strategy. This is easy to calculate, and you can show also that typically the base station is happy, it makes money, and the user is happy, it makes an utility. Let's look at the file transfer situation. So sometimes you use the web, as you know, to transfer a file. Right? Yes?
Why is the optimum better than changing the price?
Well, it requires some proof that somehow you must show that first the strategy will only consist of non-decreasing prices. There's never an incentive to decrease prices. This is obvious, right? Because if you accepted 0.5, then there is no reason for me to charge 0.4. So you can prove, take some work, that prices should be non-decreasing. If you don't accept, the client walks away. Remember, this is what we assumed. We assume that the client does not come back. So we have done, since this work, we have done some work where clients come back, right? And the clients maybe forgot what happened in the past, or maybe they don't, or maybe some probability they forget, maybe they don't, right? So in that case, the situation changes. So that was your motivation for the question, yes. So in our model, you can show that the fixed price is optimum. In the other situations, it's more complicated. File transfer. Similar situation, but now the utility is achieved only if you get the full file. So I want to download a movie or a piece of software, and the connection is utility for me only if I get the full code. If I get only part of it, I don't get any utility. That's the model. It's an extreme model. So K is the time it would take to download the file. It's unknown to the base station, because the base station does not know whether I want an MP3 an audio tape or maybe a DVD, right, or a software. But the client knows. The client knows the value of K. N is the actual duration of the game. There is no U factor in this model, so it's all or nothing, right? And the utility is P1 plus Pn for the base station. It's what you charge again. Now the situation is more complicated. What you find is that if Alice wants to download a file of duration K, Earth's Nash equilibrium, Earth's base equilibrium, is to accept to pay 0 in the steps previous to the last step. So surprisingly, she will not accept to pay 1 cent before the last time slot. And you can prove that, and I will give you a little bit about the proof. And also that in the last time slot, you should be willing to pay everything up to K, because you are willing to get this utility, K, right? The base station, the best response of the base station to this strategy is that the best strategy is a one-time only payment. So the base station will calculate one time, N, which maximizes N times the probability that K is N. So the base station will bet that the file duration is exactly N. And if it is N, then it knows that it can charge N at the last step. And then you will get N if the duration is N. And you maximize over N, right? This is a one charge only, one-time charge only. Okay, why is this true? So it is true because if you are at the last step, you know that let's imagine that the file duration is bounded to 100, right? And you have reached 100. Then the base station can charge 100. Otherwise, you will walk away, you will not get your file, right? And you have been sitting there and the file is important to you, right? The sunk cost is the sunk cost. So the last step, you know that you will get taken, right? And then you can argue by backward induction. Given that this will happen at the last step, or the next to last step, if you accept to pay some money, then your net utility will be negative, because you will be charged for the full utility the last step, but you will already paid a little bit before, right? And then you can argue by induction like this on all the steps. And given that result, this is the optimum strategy. This is very unfortunate, because if you analyze this game, what are the typical utilities of the client and of the user, of the base station? They both make very little money.
So
Yes.
considering that the base station is so much strategy, if the time taken to transfer the file is less than install, the base station makes nothing.
That's right, that's right. That's exactly right. So there are many freeloaders here. So let's say you calculate n star is 50. All the users that want a file that takes less than 50 slots will walk away for free. They will get the file, right? And so this is not very desirable. And so the base station will make very little money, typically, right? Especially if the range of possible values of k is large. This is typically small. So there is no incentive to play this game.
In the previous case where you had transfer, the solution did not depend on k, right?
Right, that's correct.
Why is that?
The solution depended only on the utility. And you can show that in that case, what you want to do is maximize the expected reward per step, for each step. And therefore it's independent of the duration. Yes, it depends. Well, it depends only on your utility per step, right? So if your utility per step is big, then the base station will collect money. If your duration is very short, well, so be it, right? You will get money for that. I think it makes sense.
Given the formulation.
Yes,
the
that's right.
formulation is not-
Right. So again, if you look at more complex models, and I could tell you a little bit about more complex models that we are looking at, the game changes. So one more complex model, as I mentioned before, is when customers come back. So, they get upset because the price is too high, but they walk away and they don't find another place to sit, so they come back and they try again, right? Then the nature of the solution changes. You don't get those features. Another way where the game changes is where in the hybrid case, where the client may either want to browse the web or may want to transfer files or do a combination of things, right? In that case, what happens? Well, so we were hoping that the situation would be nice again and that you would get a fixed price as being the optimum strategy. Unfortunately, in this mixed situation, the fixed price is an optimum only if the probability that you transfer files is small enough, right? So if you are very likely to be a web browser, then the fixed price becomes again a perfect equilibrium. So, okay, we have looked also at multi-op situations where you have multiple providers that contribute to this connection. How should they share revenue? So again, the situation gets a bit murky. So we have not found yet a simple protocol that you can easily understand and easily justify in this situation. But yes, already.
And follow-up question, my previous question. So we said that if fewer than installed slots are needed to transfer the file, the base station makes more money. If more than installed slots are needed, then the client, if the client follows your strategy, the client will quit.
That's right.
And the base station again will make
That's
more
right.
money.
That's right. It makes only
exactly installed.
it makes only when k is exactly equal to n star. Yes, which is not very good. It shows that the base station will not have an incentive to play this game, right? It's not, it does not reward enough. Yes.
So we assume that the FTP cannot resume.
Sorry.
That we cannot resume the FTP.
That's right. So once you stop, you walk away in this model, right? Yes.
You lose everything that you have downloaded.
Yes, that's correct. That's correct. So you can imagine variations where, in fact, well, I can go somewhere else to continue my download, as you do with Casa, right? If one of your sources stops, then you get the rest from somewhere else. And we have not looked at that version.
Have you considered a case where the current utility of the user is a function of the fraction of the file that is downloaded?
So that would be more like the web browsing model, right? Where what
But
you
it's not necessarily linear.
no, we have not played with other variations. Yes. So there are many variations to look at, but we have not looked at. The case of a two-hop network is quite interesting too. Let's say that you have a first wireless ad hoc network, right? You have a first wireless link. How much should you charge? then you have another wireless link. And then you end up with very interesting results. So we will write those up, and it's quite interesting. See how they share the revenues. All right, so let me conclude. I think we are reaching the end of the allotted time. So we have looked at one model for service differentiation, and we have seen that if you do just a nice game, and you let the users choose the quality of service, then what the quality of service that they end up getting depend on what the others are doing, and you end up with a prisoner's dilemma, or you end up with situations where things do not converge, or very inefficient equilibria. So this is not very good. So we propose a scheme where the quality of service is guaranteed, but the price will fluctuate depending on the demand, and that turns out to have much nicer properties for the game. In the case of a multi-provider network, we have looked again at the situation where the different providers play a nice game against one another. In that case, you end up with a very poor result for all the providers and for the users also. There is no incentive to upgrade the network. The revenues per provider will drop and will not be sufficient to justify the game and to justify trying to provide quality of service. So we have proposed a different protocol, a different game, where there's some cooperative pricing, where each provider still plays a nice game, but the revenues of the game are now a fair share of the total revenues, right? And in that case, we can show that there is a nice equilibrium, and there is a simple marking scheme for the packets to converge to this equilibrium. And we believe this is much more desirable. You have an incentive to upgrade the network, you get a fair share, and the users will be more satisfied with the service. Finally, we looked at Wi-Fi, and I presented two simple models. The web browsing, where the optimum solution is a constant price, that's very satisfactory. I mean, this is easy to implement, and it's easy for the clients to accept and to believe that this is a good strategy. In the file transfer case, unfortunately, the equilibrium is not good. It's not desirable. Nobody will like to play this game in that way, right? And that raises the usual problem with game theory that when you end up with an equilibrium that is either very complicated to calculate or very artificial looking, hard to understand why it is an equilibrium. Typically, the players do not play the strategy. They will either not find it, or not trust it, or not trust the other players to play it, right? And the predictive power of the theory then becomes very weak. So it's only when the game ends up with an intuitive equilibrium that you expect people to play the game. Otherwise, the theory starts becoming weird, right? So, and then we don't know. There's a lot to say about this too, but it's another story. So the basic objective, if you remember, was to improve the revenues by having better mechanisms in the network. Mechanisms for service differentiation, for pricing, and for sharing the revenues among the providers, right? So that's the big vision. So I don't want you to be sidetracked away from this vision by focusing on the little toy examples that I presented, right? I think the big vision is important. And I know that there's a lot of work to be done there, and don't be disappointed by the puny results I presented, right? They are just the first few steps in that direction. So we explained some preliminary ideas, a new pricing schemes that we think are rational. They provide desirable incentives, and they are scalable, right? So those are first steps along that direction. But the basic vision, I think, is important. Some references. So the work that I presented is in two papers that are online. They were presented at Allerton last month, so you can read about it. The paper on service differentiation is being written, and it will be on the website soon, I hope. Right.
Okay, let's first thank the speaker. I think we have time for maybe just a couple of quick questions. What
do you think it will take, as we look at the big picture, for these ideas to be accepted?
It will take a long time.
How long? What will it take? Decide time.
I think the first step is for the community at large to realize that there are things that can be done to improve the situation. right? And then those ideas may filter down to IETF and to Cisco and to SBC and Verizon, right? So it's a slow process. If you go today, talk to Cisco, they will not believe you, right? It takes some long process of convincing a large body of people, and eventually it filters down. But I don't have high expectations that you will see these protocols implemented in a router any day now, right? So
why would Cisco be non-believers?
because they will see as it not being their problem. The problem is a problem for the providers, right? The providers have to be convinced, and then they may convince Cisco. They say, hey, can you provide this? Or maybe some startup will provide an overlay network that will do the correct thing, right? But so I think the problem is to start convincing the vendors, and that is more difficult than convincing the providers. More difficult than convincing the vendors. They typically are less technical. They are less aware of how you can play with protocols. So it will be a difficult task.
So is there any inherent distinction between the ISPs that provide sort of core services on the internet as opposed to the ones that provide edge services? So there are a few, like AT&T and UUNet, that provide some of the core services. Are they in a different position than the edge sort of?
Yes, they are in a different position. For example, if you talk to Sprint, they will be very proud to say that their network has no quality of service problem because they run it at 15% of utilization. And then you ask yourself, gee, given that there's so much overcapacity in the backbone, why is it that we cannot access it to do what we want to do? And the answer is that the pricing of Sprint is such that they can afford to limit the utilization to 15%. But clearly this is not a good equilibrium. It's a leader-follower game where they have monopoly power, essentially. They can impose their pricing. So this is a good equilibrium for Sprint, but not for the rest of the users. So how do you change that?
So Sprint is one of the core
Yes,
providers.
one of the tier one providers.
AT&T operates
Also,
at the higher,
yes.
but they operate at the
The
higher.
same layer of Sprint. That
Same utilization,
tier one, yes.
15%.
Yes, essentially. And they will argue that they need less than 50% so that if there is a failure, they can switch over. So they need a 50% spare. And then they will say, in addition to that, we need a margin so that the delay is acceptable. And they will convince you that they cannot go more than 15%, 1.5, right? 15%. Clearly, it's weird, right? So it's surprising that the pricing justifies that. You could say, well, the incentive should be for them to provide more capacity. They will make more revenues and maybe increase their capacity further, right? But the game is not like that today. The mechanisms are not there so that users see what is happening to their packets. You don't know, right? So there is basic economic, so a lack of efficiency in the market that is caused by a lack of correct protocols. So the problem is not just economics, right? It's the intersection of economics and technology. You need the right schemes, the right protocols, maybe packet marking schemes, so that you can implement the efficient market mechanisms. And without that, you are in a deadlock. And that's where we are today, I think. So hopefully, some of you will resolve this.
Can I ask one last question?
Sure.
In the case of service differentiation, you only look at the priority queue. But if you replace it with the processor sharing where the weight given to the user depends on the class of service selected.
Now we have looked at other mechanisms and they all suffer from a similar deficiency except for one. There is one clever scheme that does not have this problem, and it is the Paris Metro scheme, where you have two parallel networks, right? They are identical, but one is expensive and the other one is cheap. The expensive network will see less utilization and therefore have better quality of service and therefore justify its higher prices, right? It's like the Paris Metro, where you have first class and second class. First class is expensive. When you go in, you can sit down. It's the same car, right? But the fact that it's expensive reduces the congestion and therefore justifies the higher price. So it's interesting. But I don't think that this is a desirable way of implementing the network because it's not efficient. Right? You have two parallel networks, and one is kept at a low utilization on purpose, right, to have a good quality of service. And you cannot take advantage of unused capacity in the network.
But
So this is
processor sharing with the same weight, this problem shouldn't be there. It should go away.
not quite. So we can discuss that offline, but you have the same interaction, even though the classes are not quite separated, right? You have a guaranteed minimum service, but the actual service that you get depends on the load in both classes. Yeah?
I think we should probably stop here. And there is no, unfortunately, there is no roundtable today because Professor Walrand needs to be back to Berkeley. So I hope we'll get a roundtable.
So again, thank you for your hospitality, and I enjoy being here. Thank you very much.